to learn the third part of number theory, which is the least common multiple and the greatest common divisor. So let's start from the least common multiples. Well, what is a common multiple? So we have learned a lot so far that about multiplications, multiples, factors, prime factorizations, right? So multiple means if I have an integer which can be expressed as another integer times n, which is also an integer, then we say that a is a multiple of b. Like for example, if I have a number 32, this can be written as 8 times 4. So then 32 is a multiple of 8. And at the same time, the number of 32 can be written as 16 times 2. So 32 is also a multiple of 16. And of course, because those are all integers, so 32 is also a multiple of 4. 32 is also a multiple of 2, right? So as long as you have one integer that can be expressed as the multiplication of two other integers, we say that this number is a multiple. Okay, this will leads us to the definition of least common multiple. So this gives us the first sentence of this definition. So if a number is a multiple of both a and b, for example, 32 is a multiple of both 8 and 16, and it's also a multiple of 2 and 4. So if there's a number that is a multiple of both a and b, then that number is called a common multiple of a and b. Right, so up to here we define what is a common multiple. Right? So basically, you have the common number that coming from multiplication of integers. But looking at here, we're trying to build something called the least common multiples. Why we're looking for least common multiples? Let's see a couple other examples. For example, if I put two numbers 2 and 3, their common multiple could be 6, right? Because 6 divided by 2 is 3, 6 divided by 3 is 2. They are all, 6 is the multiple of both 2 and 3. And then what happens if I write down another number, 18, for example? 18 divided by 2 is 9. 18 divided by 3 is 6. So 18 is also a common factor of 2 and 3. And I can keep giving further examples like 36, even 600, right, or 6,000. You can test them one by yourself, but you can also tell easily that these are all the numbers that are common multiple to the number 2 and 3. And if you just keep writing, very soon you will find that you can write infinite many of such examples. You can find infinite many of the common multiple of two given numbers. A number will go larger and larger. So there are infinite many common multiples between two given numbers, right? So this is the first thing. So which means if we're just looking for a common multiple, you can find there's no unique solution. You can find as many as you want. So, but if you go or checking to the smaller side of those common multiples, you will soon find that yes, there's infinite many going to the right hand side of number axis or approaches to positive infinity. But if you go to the left hand side of number axis where you're testing the smaller numbers, you will find that sooner or later you will reach the case that there's no other common factor. In this example, there is no other common factor that is smaller than 6. Sorry, common multiple that is smaller than 6, right? Number 5 cannot be not divisible by either 2 or 3. Number 4 is a multiple of 2, but it's not a multiple of 3. 3 is a multiple of 3, but not a multiple of 2. Similarly, 2 is not. And number 1, of course, is also not, right? And here, if we're just talking about positive integers, because I'm giving the example of 2 positive numbers, so for all positive integers, there's no other numbers that can be a common multiple of 2 and 3, but at the same time smaller than 6. So which means there do have a lower bound among all possible common multiples, that there do exist a lower bound, and it will be interesting to looking for that lower bound, or to looking for that lowest or smallest possible common multiple. So this comes our second sentence in this definition. So here we first define what is a common multiple, and then the smallest positive integer. That is a multiple of A and B. Is called least common multiple, here in short LCM, least common multiple. Right, okay, so let's keep the definition here. Let's see a couple examples. So first of all, this is the first part. Let's try to find 5 smallest multiple of number 18. So the multiple of 18 is a number that 18 times an integer n. That is a multiple of 18. And then the smallest multiple of 18, because n must be a positive integer, so which means n will start from 1. So if n equal to 1, 2, until 5, that will be the first 5 smallest multiple of 18. So that will be 18 times 1, which is 18. 18 times 2, which is 36. 18 times 3, which is 54. 18 times 4, which is 72. 18 by 5, which is 90. Okay, so this is how we find the first 5 smallest multiple of a given number in this example, which is 18. And the second part, similarly find 5 smallest multiple of another number, 24. So here I'm going to do this quickly. It's just based on the same idea that the first 5 smallest multiple is 24 times n, where n we're taking the number from 1 to 5. Okay, so over here I'm writing down the first 5 smallest multiple of number 24. Okay, then next part, let's find the smallest common multiple of 18 and 24. We will learn some special techniques at shortly, but here let's just using the most basic way, start right from the definition to try to look to find a smallest or the least common multiple between two numbers, right? Because if you want to find the least multiple, you would list the multiple of each single number from small to bigger numbers, right? Here I'm list 5 smallest number. And in fact, if you couldn't find a common factor, you can keep listing them until you find the first common factor. So right now in this example, the first 5 smallest multiples seems sufficient enough, because if you're observing your outcome from number 18, for example, you have 18, 36, 54, 72, 90, and your outcome from the multiple of 24, you have 24, 48, 72, 96, 120. So 72 is the first outcome that in common between the multiple of 18 and the multiple of 24. Right, so that is 72. So this just by simply listing all the possible multiples of the two numbers and then observing the smallest outcome from there. So that means the least common multiple, we usually just write this notation in this way. So the least common multiple LCM of 18 and 24 is 72. Right. So actually over here, if you keep listing all the multiples, you will still be able to find other common multiples later with a greater value. But as I just expressed here, the smallest common factor is a unique solution, which is 72 in this example. Okay, so then the next example, if we still use the number of 18, for example, so to write the prime factorization of 5 smallest multiple of number 18. Okay, so we already write the first 5 smallest multiple of 18. Here it's just asking us to rewrite them in terms of prime factorization. If you still remember that we learned in our previous lesson, this is a way that to breaking down a known number into the smallest elements, which are the prime numbers, because there's no further breaking down in terms of the factors to the prime numbers. Okay, the first one, 1 times 18 is just 18. Then 18, you can use factor tree if you want. Here I'm just writing in one row. So first of all, it has a factor of 2, equivalent to 2 times 9. And then the number 9, 2 is already a prime number. No way to further break down, but for 9 has a factor of 3. the 3 times another 3. 3 is also a prime number, so we are here, and we can reorganize this a little bit. So that's the prime factorization of 18 is 2 times 3 squared. And the second one is the second smallest multiple of 18 is 2 times 18. So there are two ways. One way, you do the multiplication first, you got 36. Then you can further do the factor tree or further factorize this by prime number. I would use the second way because I already know what is the prime factorization of 18. So it's simply just 2 times the known number or the known combination from number 18. And then this really just the two twos now. So it's 2 squared times 3 squared. And then similarly, 3 times 18, it's equivalent to 3 times the known breaking down of 18. So it's 2 times 3 cubed. 4 times 18, that is 4. So 4 is actually 2 squared. I can do this one step ahead. Then 2, 3 squared. So then 2 got power of 3, so it's 2 cubed, 3 squared. The last one, 5. Number 5 itself is a prime number. So this would have no further breaking down. So it's just 2 times 3 squared times 5. Okay, so this is how we write the prime factorization of the number 18. Okay, so let's see one more example. Still about the prime factorization. We're going to practice a lot of prime factorization first, because later on when you learn the formula or the algorithms on how to find the least common multiple, you will use a lot of prime factorization. The prime factorization of 72 is given. And then to determine if the following numbers are multiple of 72. Assume this is also given. I mean, you can still try to find the prime factorization of this given name, but let's assume that all such information is already known, because this example is really focused on looking for or determining the common multiple instead of practicing your prime factorization. You can still practice that by yourself, but let's just assume that this information is given as known condition in this example. So the first one, we know that the prime factorization of 72 is given here. We want to check these numbers one by one to see that if this is a multiple of 72, right? So a multiple, again, recall again that a number is a multiple of another number. It can be written in this way. So basically, all the factors from number B should also exist in number A, right? If I'm just writing some random notation as factor 1 times factor 2 times factor 3, if this is composition of all the factors from number b, then if you multiply another number n, this group is still partially the factors of number a, right? So which means if I can prove that and if I'm writing down those factors in terms of the prime numbers, that is the unique combination. Like remember the fundamental theorem of arithmetics we learned in the last class. This helps you to first determine that your factorization is unique. Then if this is already unique factorization, and I can prove that the larger number contains at least the same number of factors or even more number of factors than the other number, then this must be a multiple of that number. For example, if b is 8, it contains 3 2's. So if I multiply another 5, this means if a equal to 40, it can be written as this, right? So this if n equal to 5. So that they both have 2 cubed in 2 numbers, and number a even have more factors. So then this number is definitely a multiple of the other number. Okay, so back to here, the first example, the factors are 2 to the power of 5, 3 to the power of 3. In this example, let me write in this way to be more clear. So first of all, remember what we learned in exponents. We can write this apart because my target is to check whether I have 2 cubed and 3 squared. So which means 2 to the 5th power can be written as the power 5 can be written as 3 plus 2. And then on 3, the power of 3 can be written as 2 plus 1, right? Because I'm trying to create something similar to the known condition or to the target number that I want to check. And this, by the property of exponents, right? This equal to 2 cubed times 2 square, right? This is converting the addition on exponent over as the multiplication of the same base number. And then this is also the 3 squared times the number 3. And then if I'm reordering my target numbers together and put all other number in another place, you will have like 2 squared times 3 and times 2 cubed 3 squared. Right? I don't even need to write them further, but let me just write one more step further. Here the 2 squares for 4 times 3 is 12, so it's 12 times whatever inside this bracket. Right? So now it means that the number 864 can be written as 12 times, this is the known breakdown of 72, right? So then as long as this number is an integer, then I'm confident to say that a is an integer n times b, right? So a is a multiple of b as long as it's integer and as long as this is b, right? So this is how I prove that by having the prime factorization, I can show that this number is a multiple of 72. Okay, so let's check the second one. The second one, I can use the same way, but you can also, just by observing all the factors before you start breaking that down, or as soon as you start trying to break this down, you will find that in this number 400, it doesn't contain any number of 3, any factor of 3. Right? So it doesn't matter how I rewrite this expression with factor of 2 or 5, you won't, because this is unique, so you won't be able to make up any factor of 3 in anywhere, because this originally the number of 400 just don't have this factor of 3. So this means the number 400 cannot be written as a form of integer times 72, because you have a factor. Remember, you have a factor of 3 over here. In fact, you have 2 3's, but you have at least 1 3 over here. And if this is an integer, then the multiplication of this 2 should have contains at least 1 factor of 3. But this number 400 has no way to contain the factor of 3. So this shows that, or this proves that, the number of 400 is not a multiple of 72. Okay, so let's check the next. This one, I'm going to go through this quickly. So this is 2, 3 with another 2, 3 squared, 3 squared, 7 to the power of 1, 7. So it's 2 times 7 is 14 times 2 cubed 3 squared, right? So basically 1008 is 14 times 72, so it is a multiple of 72. Okay, so the last one, 2 squared and 3 to the 6th power. When you're observing this breaking down, you find that 2, here you only have 2 2's, right? 2 squared means you have 2 times 2 and times the rest. But to the target number is 72, you have 3 factor of 2, right? Because 2 cubed means you have 2 times 2 times 2, and then times 3 times 3, right? This is the complete form. So it looks like I'm in short of 1 factor of 2. So if I'm still trying to rewrite in this way, so at least you can stop right here, because you have insufficient number of factor 2. So this number is not a multiple of 72. It's the same idea on the previous example, that you don't have a factor of 3. It's just because in the previous example you have nothing to do with the factor of 3, so you can directly say that it's 100% sure it's not a multiple. Here, even you have the factor of 2, but it's not sufficient. So which means you are still in short of 1 factor of 2. So you're still not a multiple of that number. So if you want some further evidence, I can rewrite this number to be, if I still want to, like the first example, if I still want to construct a number that have a similar pattern to your target number, so you can first rewrite your expression as power of 2, 2 equals 3 minus 1. 6 is 2 plus 4. So yes, I can still have a 2 cubed, and then I will have 2 to minus 1 and 3 fourths power. Okay, so then, yeah, so this is 72, already have it, but then this as your n, it is no longer an integer, because this is 3 to the 4th power and divided by 2, right? 2 minus 1 is 1 over 2. Okay, so then this 3 does not contain any factor of 2, so this cannot be cancelled out or cannot be simplified. So you will have, it's actually 81 over 2. So 81 divided by 2 is not an integer. So here your n is not an integer, and this also proves that this number is not a multiple of 72. Right, so this is another way to show or to prove that it's whether it's a multiple or it's not a multiple. Right, so we can conclude from here. So the first thing we can conclude from here is that the prime factorization of a multiple of n includes the prime factor, well, the prime factorization of any multiple of 72, and here this 72 can be then generalized as any number a includes the prime factorization of a. So the multiple of a must includes the prime factorization of a, right? I just showed b equal to n times a. So all the prime factorization from a will be contained as part of the prime factorization in b. Right? We just see that in this example. For example, this is contained, like you have further factors. So this is contained or as a subset from the factor of 864. And if it doesn't work, then 72 has some factor that does not contain in, or is not a subset from this factorization, then it's not a multiple of that number. Okay, so now we're close to invent some generalized methodology to find the least common multiples. By checking all these examples with prime factorization, right, we see that first of all, every number can be written as unique combination of prime factorization, and then the multiple of, or the prime factorization of a multiple of any number a must include the prime factorization of the number a itself. So how to use prime factorization to, or of the two number, for example 24 and 90, to find their least common multiple. But where I think we're getting close to a generalized formula, but let's take one more example and see what we can find from here. So first of all, I'm going to just write out the prime factorization of the two numbers. So 24 is 2 times 12, which is 2 times 2 times 6, which is 2 times 2 times 2 times 3. So this is 2 cubed and 3. Then 90 is 10 times 9, and 9 is 3 squared, and 10 is 2 times 5. I'm going to reorder this a little bit. Maybe let us always write the smaller prime to the left hand side and write the larger prime to the right hand side. So it's 2, 3 squared, 5. Okay. So before we're moving forward, if we're just observing the prime factorization of these two numbers, 24 and 90, you can you can already conclude that, for example, what are the common factors from there? The common factors are 2, right? 2 appears in both number. 3 is also appears in, yeah, maybe I shouldn't say common factor, I should say the common multiple contains the factors of 2, because I need the common factors that cover both numbers. So 5 is also one of the factor, because as the common multiple of these two numbers, first of all, a common multiple of these two numbers must be also a multiple of the number 90 itself. And if you are a multiple of number 90, remember I just wrote down over here, that number would at least contain all the factors from the number 90. So which means the factor 5 would also contain in the common multiple. So, or in other words, all the possible factors that appears in both prime factorizations should be contained in the common multiple. So I'm taking the union of these two sets, and I summarize all the possible factors that appears in both of them. And then the power of factors must be greater or equal to, again, remember the examples we saw, if your power is less than one of at least one of the number, or at least one of the prime factorization, then you won't have a integer n to show or to prove that it is a multiple, right? So in order to have this n to be an integer, or in order to guarantee this n is an integer, that means the power of the same, so you not only just having the same factor, but the power of the same factor should be equal to, at least equal to, or better, greater than the power from number A. So the power of the factors must be greater or equal to the powers of 24 and 90. Okay, so to having these two conditions, let's see if we can construct the new number, or the least common multiple, factor by factor. So first of all, the factor of 2, right? So first of all, my common multiple, or my least common multiple, must contain a factor of 2. And then the power of this factor should be greater than both numbers 24 and 90. So the power is the maximum of these two existing powers. Right, so the power of this 2 is 3, the power to this 2 is 1. And if you're not familiar with this notation, this simply means taking the maximum value among the list inside the brackets. So the maximum between these two, the power 3 and power 1, is 3. Okay, the next factor 3, the power is the maximum, again, the maximum among the two numbers which is between 1 and 2, so it will be 2. And then lastly, factor 5 is also a common factor, and the power is maximum between, now I don't have a number of 5 here, right? So how do I take the power of 5 over here? In fact, it's equivalent to multiple another 1, and number 1 multiple to any number to the 0th power. So this means it's, if you don't have a factor of a certain number, it's just equivalent that you have this factor but with power of 0. So that doesn't matter because 0 compared to any other number, it will be, or any other positive number, it will be smaller than any other positive number. So then the maximum power of number 5 is 1, right? This is 1. Okay, so finally, altogether, if I write them, put them together, I will get the least common multiple of 24 and 90 by writing all the factors with their powers. So 2 factor 2, power of 3, factor 3, power of 2, factor 5, power of 1. If you want to see the actual number, we'll just write them apart with the actual value. So 49 by 4 is 6, so it's 360. Right, so this is the least common factor between 24 and 90. So in fact, you can check this result by yourself, or maybe let's do this together once again, and later on for all other questions you can use a similar way to check. Or I mean, you don't have to, once you familiar with this methodology, you don't really have to check every single example. But here, let me just show you how it can prove this is the smallest or the least multiple. So if I'm just listing all the common or all the multiples of number 24, it will be 24 times 1, 24 times 2. Remember we listed in another example somewhere, but we can just write them again, 70. And if you just keep writing them, you will reach 360. I'm not going to write all of them because the number of 90, the multiple of 90 will approaches much faster, because the first multiple is 90, the next one will be 180, then 270, then 360, and go on. So this, because 90 doesn't exist over here if you keep writing, 180 doesn't exist here as well, 270 doesn't exist over here, so 360 is the first multiple from the two lists, the first multiple that in common, so that it's the smallest or the least common multiple. Okay, so now let's organize what we just learned in this example to put them in plain language to organize or to summarize the methodology. So to find the prime factorization of the least common multiple, we first find the prime factorization of each number. right? We find the prime factorization of the 24 itself and the 90 itself. Even if you have like the least common multiple can be looking for even more than two numbers, can be this the common multiple among three numbers, common multiple among four numbers. So it doesn't matter how many numbers here, you always be able to find a least common multiple. And then the first step is always write down the prime factorization of each single number first. And then the prime factorization of the least. Basically, if you're able to find the prime factorization of LCM, that equivalent to how to find the value of LCM. So really here to find the value of LCM is equivalent to find its prime factorization. So the prime factorization or the value of LCM is the product of the highest power of each prime factor that appears in the prime factorization of each number, right? We're taking the highest power of each common factor, the highest power among all the target numbers. Okay, so with that, let's try to see that whether we can really use this method to quickly calculate the LCM of any given number now. In other words, we no longer need to really list all the possible multiples and then manually observing the smallest one. So we no longer need to use this time-consuming way. Now we have a much better way. So for example, as I just said, for the LCM, you don't necessarily only looking for the common multiple among only two numbers. You can actually looking for the common multiple among as many numbers as you want. So in this example, let's looking for the least common multiple among three numbers. So first of all, the first step is we need to find the prime factorization of each number given. So 24 is, we already have this, so it's 2 cubed 3. 36 is 6 square, and 6 is 2 times 3, so it's 2 square, 3 square. 42 is 6 times 7, so it's 6 is 2 times 3, so it's 2, 3, 7. Okay, so I have how many possible factors that we have in this example? The factors are 2, 3, and 7. And then how about their power? We're moving to the second step, the product of the highest power of each prime factor. So the power of 2 is the highest among 3, 2, 1, so which is 3. Prime factor 3 has power of 1, 2, 1. So it's 2. And power of the prime factor 7. 7 only exists here, so which means it's 0 in the first number, 0 in the second number, 1 in the third number, just 1. And then we write the LCM of all these numbers as the product of the prime factor 2 with the highest power. Okay, so this is your results. And of course, if you want to further expand this, you can use your calculator or use your scratch paper. So eventually this would be 8 times 9 times 7. So it's 72 by 7. So it's 504. But you really can just stop here, or up to here, you find your solution. Let's see 2 more examples. The next example is a bit generalized. So to show or to prove that the least common multiple between 2a and 2b, a and b can be any number. This equivalent to 2 times the LCM of a and b. Is it equivalent? Intuitively, yes, it is true. Like, for example, if you have a number 2 and number 3, the LCM of these two numbers is 6, right? So if you multiply 2 on both numbers here, you got 4 and 6, then 6 is no longer a common multiple, not divisible by 4, but if you multiply the same amount of 2 over here, you got 12. 12 is the common multiple, and it is actually the least common multiple. So looks like if you enlarge every single number here with a same ratio, for example by 2 times 2, then this is still true. And intuitively it is true, and mathematically we can show that it is true. So we first start with, because here we don't have a actual number anymore, it's been generalized as notation a and b, which means this works for any number of a and b. So first of all, I can still pretend to write down the prime factors of 2a and 2b first. First of all, 2a is 2 times a, right? So 2 is already a prime number. So then, if I invent a new notation, PFA, to denote that this is the prime factorization of number a, then the prime factorization of 2a is 2 times the prime factorization of a. Similarly, this number 2b, the factors can be written as 2 times the prime factors of b. Even though I don't know what are their prime factors, but I can write them into this notation to denote that this presents the prime factors. And in fact, again, go back to the fundamental theorem of arithmetic, there always exists a unique combination for each number a or b that they have a prime factorization in a certain form. So here we really just use two notations to present them, because later on we can take advantage of these notations without writing them further apart. So first of all, from the left hand side, the LCM of 2a, 2b is the highest power. Actually use equal sign. Means we're looking for the highest power of each prime factor. So how many prime factors I have? I have prime factor of 2 and a bunch of other prime factors. Here I also have a prime factor of 2 and a bunch of other prime factors. So first of all, among these two, 2 itself again is the highest power among these two factors. And then I would need to write one more step. Right, so 2 is already a common factor. I would also need the highest power of the common factor of these two terms. So it's equivalent to 2 times, right? So then 2 can be factored out because I already know the highest power, and then the highest power of, or highest power between the prime factors of A and prime factors of B. And then the highest power of prime factors of A and prime factors of B is then, from definition, the LCM of A and B. Right, so this is how I prove that the LCM of 2A and 2B is equivalent to 2 times the LCM of A and B. It's like the 2 is like a common factor that can be factored out from the LCM. And this you can take as many examples as you want to put any random number A and B over here to validate if this is true. Based on the simple example I just showed at the beginning of this question, it works exactly the way that we expected. So this means we can conclude from here that for any positive integer A and B and n, we always have the LCM of n times A between n times A and n times B equals to n times the LCM of A and B. Okay, so this is how we calculate, or how can we looking for the least common multiple. Now we're moving to the next part for the greatest common divisor. First of all, let's maybe define or just recall the definition of divisor. What is a divisor? So let A be a non-zero integer and B is any integer, then B equal to n times A. We say that, like, remember this is really just a reversed operation from multiple, right? What we learned in the past, we say B is a multiple of A. So equivalently, we say A is a divisor of B. So this is equivalent to say B is a multiple of A. Right, so for example, again, if I have 8 equal to 2 times 4, right? So 8 is a multiple of 4, equivalent to say 4 is a divisor of 8. And also there's some other way to express this relationship. Sometimes you will hear people say that number 4, for example, number 4 is a divisor of 8, right? Sometimes we already say many times 4 is a factor of 8, right? The same meaning. Or 8 is a multiple of 4, we also say that 8 is divisible by 4, right? So these are all the same meaning. It's all coming from here. It's really just the reverse operation between the multiple and divisor. So for example, let's find all positive divisor of the number 84. So which means looking for the factors, right, divisors or factors of 84. Find all possible factors. So of course, first of all, remember what I learned in the past. You can always start from the smaller integer to the larger integer, or starting from the smallest integer 1, because every number is divisible by 1 and itself, and then you can try from smaller to greater, and then all the factors are coming in pairs, so you don't have to try it all the way to 84. You only need to try it up to the halfway, because the factors coming in pairs, and up to there you will be finding all the divisors. So first of all, I start from 1. 84 equals 8 times 84. So already find two factors, which one is 1, the other one is 84. So then 2, 42, 3, 8 plus 4 is 12. 12 divisible by 3. Remember, there's a couple of shortcuts that you can check whether a number is divisible by some commonly used numbers, such as 3 or 9 or other numbers. So then this is 2, 24, 8, 28, 4, 21. 5 is not divisible, because again, remember, a number is divisible by 5, you need to have your last digit to be 0 or 5. It's neither 0 nor 5, so it's not divisible by 5. Then 6, let's try. 6 means if you have 6 and 24 is 4 times 6, so yes, divisible by 6. Then 7, you got 1 left. 14, 7 times 2 is 14. How about 8? Well, you should just try long division, or just try put 8 over here. It's not divisible. 9 is also not divisible. 10 is not. You can keep going up to 11. It's not divisible by 11. So if you further try 12, you're going back to this equals to 12 times 7, which is already presented here. And if you keep trying, you will get the same factors that you already found. So that's why I'm saying that you can stop halfway, because the factors are coming as pairs. So after here, you find all the divisor, or all the factors, or the divisors of the number 84, which are all the numbers I listed here. So then, similar to what we had for multiple, we also have a similar statement that if A is divisor of B, then every divisor of A is also divisor of B. Okay, for example, the number 20 is a divisor of 60, right? Because 60 divided by 20 is 3, which is integer. So 20 is a divisor of 60. Then the factors, the divisors of 20, for example, 4 is a factor, or 5 is a factor. So 4, for example, 4 is also, right? Because 60 divided by 4, you will definitely get a integer solution. So 4 is also a divisor of 60, right? And this is very intuitive, because if a number is already a divisor, then the breaking down, or the further breaking down of its factor would definitely be a divisor to this number as well. And further, if another number c is a divisor of the two number a and b, then c must also be a divisor of a plus b and a minus b. So this, for example, well, I don't even need to write the example. Like, for example, if c is written as, if c is the divisor of a, c can be written as a times integer n. And if c is a divisor of b, c can also be written as b times another integer m, for example. Then a plus b or minus b putting this way. Because c is a divisor, so a and b are multiple of c. So c is a divisor, then number a can be written as an integer times c. And similarly, number b can be also written as another integer times c. So then a plus b or a minus b would be written as n times c plus or minus m times c. And then c is the common factor, so it's m n plus or minus m times c. Now, if m and n must be integers, then the sum and subtraction of the two integers are also an integer. Doesn't matter positive or negative, it's an integer. And as long as this is also an integer, that means c is a divisor of a plus b and a minus b. So now let's define what is the greatest common divisor. Now you probably find that this is also similar to the least common multiple. It's just because the multiple must be a number greater than the original number, so it can go as large as possible, so then it's reasonable to find the lower bound of the common multiple, so we are looking for the least common multiple. Now, oppositely speaking, divisor would be a number that's smaller than the original number, and if there exists a common divisor, it will getting smaller and smaller, so which means there will be an upper bound exists, and it will be interesting to looking for this upper bound, or in other words, looking for the greatest common divisor. And in fact, the greatest common divisor could possibly doesn't exist, or equals to 1, which means there's no other common divisor other than the number of 1. Because simply speaking, if you have two prime numbers, or at least two numbers prime to each other. So you really have to be a prime number as long as the two numbers do not have a common divisor. For example, 3 and 4. Right? The only possible number satisfy this condition is 1. Only 1 is a divisor of 4 and same time divisor of 3. You cannot find any other possible numbers. Then this greatest common divisor will have to be 1. So there's no other number greater than 1. So go back to here. We're still looking for the greatest common divisor, but it is possible that this greatest common divisor is just 1. So this is the greatest positive integer that is a divisor of both a and b. So it's called the greatest common divisor, GCD. So how do we find the common or the GCD between two numbers or between a bunch of numbers? So similar to how we find the methodology for looking for the least common multiple, we also start with a couple examples, and then we'll try to looking for the pattern from the example to see if we can summarize the methodology from here. So the first example, we will also just simply coming from the definition itself by listing all the possible divisors to see if we can find any pattern. So first, let's list all the positive divisor of number 18. So 18 is 1 times 18. It's also 2 times 9. It is also 3 times 6. 4 is not a factor. 5, no. 6, you already have 6 over here. So all the divisor, let me use letter D for the short of divisor. So divisor of 18 is 1, 2, 3, 6, 9, 18. Okay, then let's list all the positive divisor of number of 24. Okay, so 24 is once again 1 times 24, or 2 by 12, 3 by 4, 3 by 8, 4 by 6, 5, no, 6 already have it. So we have number 1, number 2, number 3, 4, 6, 8, 12, 24. So here are all the positive common divisors, or all the positive divisors of these two numbers, 18 and 24. And if we're just observing the common ones from these two lists, right, we'll just mark them down one by one. 1 is in common, 2 is in common, 3 is in common, 4 is not, 6 is in common, 8 is not, 9 not, 12 not, 18 not, 24 not. So we actually have 4 factors that are in common between these two numbers. And then the greatest factor among this list is obviously number of 6. So the greatest common divisor between the number of 18 and 24 is 6. Okay, so this is the first example by simply listing all the divisors or listing all the factors and looking for the greatest one. The next, let's check the prime factorization and check whether the following numbers are a divisor of that number. Prime factorization of 1944 is 2 cubed 3 to 5th power. Determine whether following numbers are divisor of this number or not. First one, 108. Again, if we just assume that we already know the prime factorization of 108, then let's check whether this is a divisor of that number. And we've been practiced through the least common multiples already, and then we had a lot of examples of the common divisor as well. So simply speaking, you probably already get a sense that if one number is a divisor of the other number, which means after prime factorization, all the factors should be contained already in the original number. Here, when I say contained, which means if your original number has 2 to the 3rd power, and you're checking the number that has a 2 to the 2nd power, then number 4 is definitely a divisor or a factor of 8 because you contains all the factors that the number 4 has. You have even more factor than him, right? So which means this to be generalized in mathematics, this simply means you have the same factor and your power 3 is greater than his power 2. So that means that you contains the factors that coming from the smaller number. So that means if we just compare the power to the prime factor, and if we can show that the power of this number is smaller than the target number or the number in the question, then we can claim that this is a divisor. So to number 2, the power of number 2, I have 2 is less than 3 here. Power of 3, I have 3 is less than 5. So it is divisible, or it is the divisor of the target number 1944. And if you want to validate this, you can just use your calculator to do the division and to see if whether the outcome is an integer or not. Okay, the next, if I have number of 45, which can be written as 3 squared times 5, here I can still compare power of 3, no problem. But power of 5, you find that there's no power of 5 in 1944, and there is a power of 5 in the number 45. So this means this number 45 cannot be a factor or cannot be a divisor of this number, right? Because it contains a factor that you don't have. Then it doesn't matter how you're dividing that number, this factor of 5 cannot be cancel out, or it does not contain in your original prime factorization. So if a factor, maybe I give another simple example, number of 12 has factor of 2, 2 and 3. Number 10 has factor of 2 and 5. So 2, you have more 2's than 10, which is fine, but you don't have a factor of 5 from the number of 12. So then if you use 12 divided by 10, you won't get, it's not divisible clearly. It's 1.2, or it's 12 over 10, which is 6 over 5. So it's not an integer. So it's not divisible. And this can be either explained as the division, or now it can also explain by comparing the prime factors. So if you have a factor that does not exist in the bigger number or the original number, then you are not a divisor to that number. Okay, the last one, if I have 48, which can be written as 2 power of 4, 3 with power of 1. Here, if I'm checking power of 2, I have 4 from 48. I have 3 from the 1944. So the power here is greater than the original number. So this also indicating that they are not divisible, right? We already see a lot of examples when we learn the common multiples, or in multiple, or in divisions. And then in terms of the prime factorization, you have more 2's than you originally having here. So when you do the division, imagine that when you do the division, you will have some 2's left behind, and this will make your outcome to be a non-integer. And if your outcome is not an integer from the division, then you are not divisible, such that this number is not a divisor. Okay, so now we can try to see that if we can have a generalized method to looking for the greatest common divisor. One more example. So the prime factorization of the number 360, this is given as a known condition just because we're focusing on different aspects. So let's assume that we already know how to looking for the prime factorization. So we have prime factorization of these two numbers. So first of all, a divisor with power of 2. Here, this means if there exists a divisor of both number, then this divisor, and if this divisor consists at least a prime factor of 2, then the power of its prime factor of 2 cannot be greater than the known number. Two to the third power, or 2 to the fourth power. So it cannot greater than 4. Right? For example, if I do have a number contains a prime factor of 2 and the power of this 4 is greater than 4, so that could be 5, and number of 2 to the 5th power is 32, then you can test that 32 is clearly not a divisor of 48, and it's also not a divisor of 360. So which means if you're exceeding the greater of these two numbers, so not even the number of 4, right? So number of 3 is also the upper limit. So if you have 2 to the 4th power, you have 16. 16 is a divisor of 48 because you have 2 to the 4th power. But 16 is not a divisor of 360 because you can either do the division by yourself, or you can imagine that you only have 2 to the 3rd power over here. So the power of 2 cannot be greater than both numbers here, so it's cannot be greater than the minimum of these two powers, which is 3 in this example. Okay, so that the power of 2, this, and power of 3 cannot be greater than, this is power of 2, this is 1, so cannot be greater than 1. I'm always taking the smaller. Remember, different from the LCM, I'm taking the maximum power. In GCD, I'm taking the minimum power. That's the difference. And the power of 5, this is similar because I have 5 here, the power is 1. I don't have a 5 here, that means the power is 0. And now it matters because we're taking the minimum, so 0 matters. So here the minimum power of 5 will be 0. So then the GCD of these two numbers is again the prime factorization, putting together with all the factors and their powers. So factor 2 is power of 3, factor 3 with power of 1, factor 5 with power of 0. So it's 24. So the greatest common divisor of these two numbers is by looking for the minimum of the power of each factor, including 0, and then putting together as the prime factorization. Okay, now let's try to summarize what we found on the methodology of how to finding the greatest common divisor in plain language. So we can find the greatest common divisor with following steps. Similarly to the least common multiple, we also define the prime factorization of each number as the first step. And then second, to identify the prime factors that appear in all factorizations among all the numbers. And then the next step is different from LCM. In LCM, we're looking for the maximum power, but in GCD, we find the smallest power. And this, in fact, includes 0. Looking for the smallest power. And then the last is put them together, so multiple the powers of primes that we found in the above steps. And there's one more statement. Remember over there I gave another examples that for two numbers you not necessarily always able to find their GCD, a non-equal to 1 GCD for any given two numbers. For example, number 4 and number 3, even though 4 is not a prime number, but the GCD of these two numbers, there's no other common divisor that is other than 1, which is the smallest possible common divisor. And in fact, any two numbers will have a common divisor of 1. It's just about whether this is the smallest one or this maybe not the smallest one, or whether this is the greatest one or it's not the greatest one. So in such case, actually we have many such cases. In such case, if two integers do not have, this means they do not have prime factor in common, right? The prime factor is 2 and the prime factor is 3 to the second number. Nothing in common means the smallest power will be 0 to each factor. So that's how eventually you get GCD of 1, because it's 2 to the power of 0 times 3 to the power of 0, so it's just 1 times 1. So if the two integers do not have prime factors in common, right? Such in this case, you don't have prime factors in common, then their GCD always equal to 1, and we call the integers are relatively prime. Okay, so this is an important name that you will hear this in the future when people talking about, or especially in number theory, when people talking about two numbers are relatively prime. That means these two numbers do not have a common, or do not have prime factors in common. And in fact, the number itself don't have to be a prime number for itself. Like in this example, number 4 is actually not a prime number. But as long as you don't have the same prime factor in common, then we say that we call that these two numbers are relatively prime. And then we also have a similar property that we had in the least common multiple. So let A and B are two positive integers. Every common divisor of the GCD of A and B. Every common divisor of A and B is a divisor the GCD of A and B. So this is quite natural that if a number is a divisor of A and the divisor of B, it must be smaller than or equal to the greatest common divisor. And if it's smaller than or equal to the greatest common divisor, then this number must be a divisor of the common divisor. And also, every divisor of the GCD is a common divisor of A and B. You can also write as many examples as possible if you want to verify if this is true. So basically, right, if you're already a divisor of GCD, then you will always be a common divisor of each number A and B. Okay, let's see some more examples to practice how to calculate the GCD between two numbers. So first of all, looking for the GCD of between 27 and 39. Step 1, write the prime factorization. 27 is 3 times 9. It's actually 3 cubed. 39 is 3 times 13, and there's no further factors. So it's 3 times 13. So then the common factors are 3 and 13. And then I'm looking for the smallest power. So the power of 3 would be minimum, the smallest power. Minimum of 3 and 1, which is 1. And then the power of 13 is minimum of, there's no 13 over here, so the power is 0. There's 1 13 here, so the power is 1. But then the minimum power will be 0. Right, so then the GCD is the possible factors in common and the minimum power, which is 3. Now here, there's one, in the next example, we'll show the simplified way, because if you don't have a factor in common, you can see here, if you don't have a factor in common, you must have somewhere with a power of 0, because the first in here, number 27 doesn't have factor of 13, so the power to 13 always be 0. So then if you don't have a factor in common, it will contribute a power of 0 somewhere. And then when you take the minimum, if you already have a 0 somewhere, then your minimum must be 0. And then it ends up that your GCD will always have a 0 power to that factor. So unlike the LCM that you take the maximum, so you need to list all the possible factors. Here, if you only list the common factor, that will be sufficient enough, right, to get your answer of 3. So for example, let's see another example. So the GCD of 163. 100 can be written as, it's 10 squared, so it's 2 squared, 5 squared. 63 is 3 times 21. 21 is 3 times 7, so it's 3 squared 7. And then let's compare the factors from the two numbers. This one, 100, has factor of 2 and 5. 63, you have factors of 3 and 7. Nothing in common. So there's no common factor such that the GCD, such that these two numbers are relatively prime. And the GCD is anything with a zeroth power, so GCD is 1. Okay, the third one. This time we have the number already written in terms of or in forms of the prime factorization. So we have so we have two numbers set already written in prime factorization. So then the first step, check what are the common factors. Is 2 in common? 2 is not, because the second number doesn't have a factor of 2. Is 3 in common? 3, the first number doesn't have a factor of 3. 5 is in common, and 11 is in common. All right, so then the power is the next step to determine power of 5 is the minimum between 2, 3 and 2, which is 2. Power of 11 is the minimum between these two numbers, which is 2 and 1. That is 1. So then the GCD is the product or the multiplication of the common factor with their minimum power. So common factor 5 with the minimum power of 2, common factor 11 with power of 1. Right, so you can further write this into an integer, but this is how you find the GCD. And the last example, I'm going to leave the proof to yourself, because when you see the example, you'll find that it's very similar as we just proved to LCM. So in GCD, we have a similar conclusion. So for example, similarly in GCD, you can try to prove that the GCD of 2A, 2B, whether it's equivalent to 2 times the GCD of A and B. Right, again, you can write the prime factorization of 2A as 2 times the prime factorization of A, and then keep going the similar way that we proved this in LCM. So once you proved this, the conclusion is that for any positive integer A, B, and N, we have GCD of N times A, N times B is equal to, you factor out the common integer N, then taking the GCD of A and B.